Okay. All right, so we are going to continue working through lecture set number 4. Lecture set number 4 is devoted to studying one-way ANOVA, so one-way analysis of variance. So today what we're going to do is essentially look at the rationale behind why we can study variance when we want to talk about differences between population means, which has been more or less the type of inference that we've been focused on so far in this class. So the one-way ANOVA is a extension of the 2 sample hypothesis test that we talked about in lecture set 3. In that it allows us to test for a difference among population means. But again, it uses variances rather than the sample mean values themselves to detect that difference. Well, yeah, you'll see what I mean by that momentarily. We finished off on Thursday studying the F distribution. So the first part of lecture set 5 was a introduction to, or a description of, and examples of how to use the F distribution to find critical values and to find p-values. So our one-way ANOVA hypothesis tests are going to be based off of the F distribution. That is, the test statistic is going to be an F random variable. And as a result, we're going to need to know how to use the F table and the F distribution to find critical values and p-values so we can make a conclusion about our null hypothesis. Okay, so we finished off looking at 4 examples. The first 2 are critical value examples and the second 2 are p-value examples. Very briefly, as a reminder, the F table is a table with 2 degrees of freedom, and it works very similarly to a T table, except that you have a 3-way match, DF1 to DF2 to the significance level. So then you can find your critical value or your p-value. But once you have the 2 degrees of freedom located, it's exactly like a T table in that you either pick your significance level or you look for where your test statistic falls within the values on the table. So I'll show more examples of this once we get to the ANOVA illustrations, but we also, again, have the 4 examples that are shown on slide 7. All right. So as I had said just a few moments ago, one-way ANOVA is an extension of a 2 sample t-test. So we have seen hypothesis tests for one population mean. So we've asked questions like, is the population mean different from 14? Is the population mean less than 6? This kind of thing. Then we saw illustrations where we compared 2 population means. So is the mean of population 1 bigger than the mean of population 2? Is the mean of population 1 different from the mean of population 2? This sort of idea. With one-way ANOVA, what we are doing is we are taking 3 or more population means and we are comparing them to each other at the exact same time. And the goal is to determine if a difference exists among the set of population means that you were studying. All right, so we'll start off with an illustration of what a data set might look like when we want to submit it to a one-way ANOVA. So on slide 8, we have data that measures the data set counts the number of whales that have gotten entangled at certain depths. And then it gives you the average length of the whale in meters at each of those depths and the standard deviation of that length. Okay, so we have 4 different depths, 0 to 49. So we could think of this as okay, so we could think of this as population 1, which is your 0 to 49 meters of depth. Yeah. And then our population 2 would be 50 to 99 meters. Population 3 would be 100 to 149 meters. And population 4 would be 150 to 199 meters. Okay. Now the question is there a difference between the population mean length of the whales at each depth? Okay. So we might ask, okay. So is there a difference between the population mean? I've written mu j, one mean for each population, 1 to 4, lengths of the whales entangled at each depth. So up until this point, our only way of handling this type of situation would be to do comparisons of each pair of means. So we could use a 2-sample t-test and compare mean 1 to mean 2. We could compare mean 1 to mean 3. We could compare mean 1 to mean 4, mean 2 to mean 3, mean 2 to mean 4, mean 3 to mean 4. So we could do separate t-tests for each comparison. As we will see, this is actually something that we will return to, this idea of doing these separate style of t-tests. We'll look at it in a far more efficient manner once we return to the idea. But at this point, given the question that we are asking and the structure of the data that we are working with, we would like to be able to perform this comparison in a more efficient way. And this is, again, what the one-way ANOVA procedure is going to allow us to do, is answer this kind of question in a using one hypothesis test. All right. So the analysis of variance procedure or procedures are actually a suite of different tools that we can use to compare the means across 3 or more populations. In this class, we're actually going to study 3 different types of ANOVA. So analysis of variance actually refers to a larger pool of methods than just what we are studying in lecture set 4. Okay. Again, the name of the procedure can be misleading because we are using the variations to make a statement about the means. So analysis of variance uses variances from the populations that we are studying in order to compare the means of those same populations. So these tests are about population means, hence the description of them being an extension of the 2-sample t-tests. All right, so the question is, we're going to analyze variances to make a statement about population means. How would this work and why does this work? All right, we're going to consider 2 very simple illustrations to try and illustrate why we can analyze variances to make statements about population means. In the diagram shown on slide 10, we have 2 samples of data, sample 1 and sample 2, and they are colored as black circles for sample 1 and red crosses for sample 2. Okay, so the mean of sample 1, the sample mean is 16.87, right? So this is going to be right about here. And the mean of sample 2 is 25.32, which is going to be right about here. Okay. Now the question is, does it appear like these 2 samples are different? All right, to answer this question, first off, you have to consider that if we were visualizing this data without the color, and without the shape recognition. So we would have one pool of information. That's the first part. So think about, even though I've separated them by color to illustrate what we're getting towards, imagine that we have these 10 points on the same line. So they're plotted where they are on this graph, but they are all the same shape and color. Can you tell that there's two different samples of information here? Well, the answer to that question would have to be no. It looks like one large sample. So even though the means, the sample means, are fairly spread apart, they're about 10 units different in their value. Because each sample has a high within sample variation, the difference between those means is masked, so you can't tell they're different. Now, when I say within sample variation, what I mean is the variation between the small, or the variation within the red and the black groups separately. So we can kind of think of, if we were to take the smallest, so the within sample variation, okay. So when I say within sample variation, I actually just mean the standard deviation, or the variance rather. It would be the variance variation. I mean the variance for each sample separately. So when the samples, so that's S2 squared, standard deviation of sample 2 squared. So the variance of sample 2. So when you have different samples of information and you compare the variations of each sample separately, if that variation is very large, it's going to push the values further away from each other. And that means that they might cross over with other samples. And when this happens, like it has in this illustration here, it masks the difference between the samples. So this is our first indication that studying variation can be useful when trying to determine if the means of the different populations are different. Does that make sense? Any questions? Okay. All right. I'll just quickly note down the same thing for the other sample. So it's going to be a little bit trickier, but okay. So our within sample variations are just the variances of the samples, which we know how to compute. We've been doing this in our reviews, and we did this for 2 sample tests. What, again, this example is showing us is that if you have a large within sample variation, that can mask the differences between the samples. All right, so here's the counter. So very same setup, slightly different sample mean. So same population mean, but just a slightly different sample. So here is going to be X bar 1. And here is going to be X bar 2. Okay, so now the question is exactly the same. In this illustration, can you tell that there's a difference between the samples? Well, again, if we say that the within sample variation is S1 squared, and the between sample the within sample variation here is S2 squared, you can see that what's happened, the only difference between this illustration and the previous illustration is that our samples have now decreased dramatically in variance. So sample 1 and sample 2 have a much smaller variance in this second illustration. And as a result, it now looks like those samples are different sets of values, and hence they have different means. Okay, so we're able to make these determinations by only studying the variation. So we know, what we now know is that if we decrease the within sample variation, this can show separate samples of data, which in turn can help us to determine that the means for each population from which these samples were drawn are different. Any questions? All right, so let's try and establish what we're going to be looking for in general when we're using these analysis of variance techniques. So on this illustration, I've plotted the two examples together so that we can compare the differences directly. So the means are going to be at roughly the same points. Well, not so much, like say X bar 1 here. Yeah. X bar 2 here. X bar 2 here. Okay, so we've already established the definition of the within sample variation. So we know that the within sample is simply the variation within each sample directly. And this is done this is found using the normal formulas. So formula for variation or formula for variance. Okay, so we can clearly see that in the first illustration, we have very small within sample variations. In the second illustration, we have much larger within sample variation. Or sorry, in the second illustration, it's small. In the first illustration, it's large. Sorry. Okay, and we can see that when the within sample variation is large, this indicates that this masks the difference between the population means. Whereas when the within sample variation is small, this can illustrate that we do have a difference between population means. All right. In order to determine how big or how small the within sample variation needs to be, in order for us to say there is or is not a difference between the population means, we need to compare it to something. So we also define what is called between sample variation. So the between sample variation is essentially the variation between the sample means. Okay, so we define this between sample variation . Okay. And we say, and what we do is we basically compare the between sample variation, so the variance of the sample means directly, to the within sample variation, which is just the variances of each sample. And then we can say if the between sample variance is big relative to the within sample variation, that would suggest that there's a difference between the population means of interest. Okay. So again, we're analyzing two kinds of variance, the between sample variation and the within sample variation. And we're using a ratio of those two variances to determine if the population means are statistically different from one another. And again, this is simply done by comparing the two variances. So if you have a large between sample variation and you have a small within sample variation, when you compare those two, when you divide one by the other, you're going to end up with a larger value, which suggests that you have a difference in population means. If you have a large between sample variation and you also have a large within sample variation, when you compare them, so you divide one by the other, you're going to get a smaller value, and that's going to indicate that there isn't evidence of a difference. Okay. All right. Any questions? All right. So all of the ANOVA procedures that we are going to study in this course are based off of this same idea. So essentially, every ANOVA procedure has the same foundation. All that we do is we change the types of variances that we are studying. So we're going to see an example of three different types of variance when we define the one-way ANOVA procedure. When we extend to the completely randomized block design in lecture set 6, we're then going to see 4 different types of variation, but they're all very closely related to one another. Essentially, all you're doing is you're taking overall variation, which I'll define momentarily, and you're breaking it into different parts. And then you're comparing those different types of variation to compare population means. All right. So our first ANOVA procedure, or the focus of this lecture set, is the one-way ANOVA, which is the simplest kind of ANOVA. Okay. It's called a one-way ANOVA because it compares a single variable from a single factor. So essentially what that means is you're measuring some variable, for example, the length of the minke whales, and you're splitting the population based off of one grouping factor or one characteristic. As we extend to different types of ANOVA, for example, we'll consider a two-way ANOVA. What happens in that situation is you have one variable that you're measuring, but you're grouping the population based off of 2 different characteristics. All right. So as we extend to different definitions of ANOVA, what we're mainly going to be doing is just adding in additional factors that separate the population into different groups. All right. So again, an illustration of these definitions, the variable is what we are measuring, which is the length of the minke whales. Okay. The factor is how we are splitting our samples into groups. So in this case, our factor is depth, of which we have 4. The number of levels in the experiment refer to the number of different groups that are being formed by that factor. So in our situation, we have one factor, which is the length, which is the depth. And that factor has 4 levels, which are the 4 different what would be the word, like ranges, sorry, the 4 different ranges of depths that we are considering. Okay, any questions? There's a lot of different little definitions that come in. We'll look at examples later, but it's good to get a sense of what each of these things are and how they differ right off the start. Oh, cool. I know you can do that. Okay. All right, so the variable of interest is also referred to as a response variable. The rationale for this will become more clear when we actually see the one-way ANOVA model. And I'll just make a note here. We can compare this to compare to a regression model. Okay. So the one-way ANOVA procedure, there's actually a statistical model that we use to represent the outcomes. In that model, the variable of interest turns into what is called the response variable. So the variable of interest is a function of the group means, and that's why we call it a response variable. And as we're going to see later in the course when we study regression, we can actually show that the one-way ANOVA is a special case of a regression model. In fact, all ANOVAs are special cases of regression models. And that again is why we can also refer to the variable of interest as the response variable. Okay, so whatever it is that we are measuring is the variable of interest and is the response variable. Those are the same things. Okay, the factors are again the variable that is being studied. So it's the variable that is splitting the variable of interest into different groups. Okay. The factor levels are the different levels of the variable that we are considering. So for example, the 4 steps. Okay, and the treatments are the possible factor level combinations. This is going to have more meaning when we get to the CRBD and the two-way ANOVA. In one-way ANOVA, this is analogous with factor levels. Okay, so we have a number of different terms that all define the exact same thing. That's one of the key takeaways from this slide. In terms of the variable of interest, this is often called a response variable. So variable of interest, response variable, these are usually the same thing. The factor levels or the factors, again, is the same thing. Typically, we refer to the factor as the general variable that's going to split the data into different groups. So in the case of the minke whale illustration, the factor is the depth. The factor levels, so there'd be 4 levels, and the factor levels are the separate depths, so those ranges. The treatments are combinations of the factor levels, which in the case of one-way ANOVA doesn't actually mean anything. They are the factor levels directly. But when we move to a completely randomized block design or a two-way ANOVA, the factor levels can interact with each other, and that creates different treatment combinations. So for now, you can consider these things synonymous, but once we get to the more complicated designs, this definition of treatment will come into play because we have different factor levels interacting with each other. All right. Sorry, any questions? All right. I'm now going to provide some definitions for the actual data itself and the summary statistics that arise from the data. For the most part, we don't have to dwell too much on these definitions, but it is beneficial to understand each of these different terms such that you can understand how the calculations for an ANOVA would come into play. On assignment number 3, which hasn't been posted yet, we're still on assignment 2. But on assignment number 3, you will be required to perform the all of the calculations that would build an ANOVA table from the raw data. So again, having an understanding of how these definitions work is going to be useful in terms of completing that type of exercise. Of course, in lab, when you're provided with data, you're going to be able to use SPSS to do these calculations, so it isn't necessary. And of course, on tests, we're not going to be asking you to do that intensive of a calculation. So it's really just for the assignment that we need to know how to do this in terms of your grade. And then, of course, for your general knowledge and understanding, it's beneficial to be able to read these type of formula. All right, so when we're working with ANOVA data, we typically separate our observations into different groups. So we might have population number 1, of which we sample N1 values. Okay, so that's what the first row of this table is showing us here. So this is a sample of size N1, right? And that's what's indicated in the second column as well. So we have X1 to XN1, where the subscript 1 refers to the fact that this came from population 1. Similarly, from population 2, you have a sample of X1 to XN2, 2. This is, again, referring to the fact that you have a sample from the second population. So that second digit, X11, XN11, that's an indicator that it's from the first population. And this is similar for all of the different populations from which we might sample. Each of those samples has their own sample size. So sample 1 has a size of N1, sample 2 has a size of N2, sample 3 has a size of N3, etc. Each of those samples have their own sample mean, which we designated X bar subscript 1, X bar subscript 2, X bar subscript 3, etc. And each of those samples are going to have their own standard deviation and their own variance. And again, we have S1 for sample 1, S2, sample 2, etc. Very similar to what we did in the two-way ANOVA case. We're going to assume that each population has their own mean, which we designate as mu1, mu2, mu3, mu4, etc. Okay. We let capital TJ represent the total for the sample. So that just means that capital TJ is the sum of every single observation in the sample. Okay. So TJ is equal to the sum from I equals 1 the sum from I equals 1 to little nk, or rather little nj, I'm just going to move this over so I can write it properly. Okay, so TJ is the sum from I equals 1 to little nj of x I j. Okay. This is the same thing as little nj times x bar j. Okay. So TJ represents the total for the sample. So it's just all of the values in the sample added together. Okay, the total number of observations in the entire experiment is the sum of each individual sample size, which makes sense. So little n defines total observations across the entire experiment. And x bar without a subscript is the mean for the entire experiment. So the mean of all of the different values that we have collected as one whole group. All right, so we use these definitions in order to understand how to compute the variances between and within the samples. So I'm going to formally define those in a few slides. Before we get to those strict definitions of the variances, we're going to study we're going to look at the model and the different assumptions that are associated with that model. So up until this point, Just as a refresher, yeah. Sorry, I was just looking at the organization of this. Okay, so up until this point, what we have done is define the F distribution. We have explained why we can use variations to talk about differences between the means, and we have done preliminary definitions for the experiment. So we've talked about response variable, factors, treatments, and then we looked at the definitions of the actual values that we would collect. We're going to return to those definitions when we formally define each of the types of variances. Before we do that, we're going to look at some strict definitions for the ANOVA experiment. And in particular, we're going to talk about the ANOVA model, which I had referenced before. And we're going to talk about the associated assumptions of the test. And then we will look at the construction of the hypothesis test directly. Okay, so the model, the one-way ANOVA model is given on slide 16, and that's shown in equation 1. Okay, so in this model, we assume that the data have the following formula. So we're saying every value in the population is equal to its population mean plus epsilon ij, where the epsilon ij is a normally distributed error. Okay, so what this essentially means is that from 1, we can write xij is distributed normal with mean mu j and variance sigma squared. Okay, so what this means is each value in the population has mean mu j and is normally distributed, right? So visually, this means that what we are assuming is that all of the data can be structured as follows. Okay, so we can visualize this. So we might have mu1 here, mu2 here, mu3 here, mu4 here. Okay, so this assumption is telling us all of the data is normal and the data can be separated by their own mean, but the variance for every single value is the same. So that means that if we were to take a normal curve, maybe something like this, okay, we can place this curve at any point along this axis. So we might have one here. We'll have one at mu2. We'll have, or one at mu1. We'll have one at mu2, one at mu3. And sorry, this should be mu k here, and one at mu k. So the assumption is telling us, or the model is telling us, when we use a one-way ANOVA, we assume every single value in the population is normally distributed, but the values can belong to different normal distributions that are only different because of the mean that they are centered at. So the variation is identical across all 4 of these illustrated populations that I have below, but the variances are exactly the same, and the data are allowed to belong to one of those K different groups. All right, so this is the assumption we make, or the key assumption we make when we fit this, this model. So when we use one-way ANOVA, this is what we are assuming to be true about the population. Questions? Does that make sense? So from the model and from that model given on the previous slide, we can write down the following 4 assumptions. Assumption number 3 and assumption number 4, 3 and 4, they follow directly from the definition given in equation 1. So each xij is normally distributed and each xij has the same variance. Okay, so that's what the model is telling us directly. We assume all of the data in the population, or all population values, are normally distributed, and they follow, or they are normally distributed with the exact same variance, but they are allowed to belong to distributions with different means. We're also going to assume that we collected simple random samples and that the information in each sample are independent. So we have independent simple random samples that are collected from normally distributed populations with the same variance. That's essentially what the model is telling us. And these are the 4 assumptions of our ANOVA procedure, or of the ANOVA procedure. All right. So just like before, we will need to check these assumptions. The simple random sample and the independence assumption, in order to check those, we have to know where the data came from. All right. So just like when checking the simple random assumption, the simple random sampling assumption in the previous lecture sets, we had to know where the information came from in order to check this. To check the normality and the constant variance assumption, we can use a normal probability plot to assess the normality assumption. The normal probability plot is actually going to be built using the residual terms, which I will define at the start of lecture set number 5. So we're going to talk about assumption checking for the ANOVAs in a separate part of the course. We're going to describe the assumptions first, give a general description of how you can check it, and then we'll look at how we would do this directly. Okay. To verify the constant variance assumption, we can do a number of different things. So we can create side-by-side box plots of each of the different groups and check to see if those box plots have the same length. That would be one way of doing it. We can also use what is called the rule of 2. The rule of 2 takes the largest standard deviation in the from the samples that we are using and divides by the smallest standard deviation from the samples that we are using. And if it is less than 2, then we can say that the variances are considered equal. We can also use what is called Levene's test, and this is what SPSS does for us directly. So Levene's test is essentially an ANOVA for variances. So it says, it assumes that all the variances are equal against the alternative that all the variances are not equal. Okay. And then for Levene's test from SPSS, we can get a p-value. We can compare the p-value to alpha directly. If it's less than alpha, this would suggest not all variances are equal. And if it's greater than alpha, this would suggest that there's no evidence that the variances are not equal. So again, we have 4 assumptions: SRS, independence, constant variance, and normality. SRS and independence would be checked given information about where the data came from. We're going to assess normality using a normal probability plot, which is essentially what we did, is what we use for our t-test as well. Those normal probability plots will be constructed using what are called residuals, and I'll come back to define those later. And for checking for constant variance, we have a number of different techniques that we can use. In SPSS, they give the output from Levene's test directly. So when using SPSS, you can just use the result from Levene's test to determine if there is or is not evidence of constant variances. Otherwise, we can do things like use the rule of 2. It's very popular. I'll show you an illustration of this a little bit later. Or we can use like side-by-side box plots to compare the deviations of each of the samples. Any questions? All right. Okay, so let's return to setting up the ANOVA. So we defined the different components of the data that we are going to be using when we want to run an ANOVA. So for example, we have the Xij, X bar J, Nj, etc. Our ANOVA procedures compare variances between the groups to variances within the groups, which we also defined earlier. We write these different variants, or these variances are found by using a decomposition of the sum of squares. Okay, so we're going to calculate our variances from these sum of squares, these sum of square values defined in equation 2. So we have 3 different sums of squares in the one-way ANOVA case. We have SST, we have SSTR, which is the treatment sum of square, and SST is the total sum of square. And then we have SSE, which is the error sum of square. Okay, so we can see from the definitions here, SST is the sum of each observation in the data minus the overall mean. Okay, so this is the total sum of squares for the entire data set. So this would be the numerator of the variation for the entire data set. Okay, so from this, so SST leads to total variation, right? So if we take the SST and we divide by the overall sample size minus 1, we now have the variance of the entire data set that we are studying. So the SST is the numerator for the variance of the entire data set. The SSTR leads to between sample variation. Okay. And you can see why this is true if you look at the formula here. We have each sample mean, and here we have overall sample mean. So you can see like what the SSTR is doing is it's calculating the square difference between each sample and the overall sample mean. So it's finding the variation among the sample means directly, which is between sample variation. The SSE is our path to the within sample variation. Okay, so SSE is going to lead to within sample variation. Okay. And then just to be clear here, the arrow means leads to. Okay, so the arrow is saying SSTR leads to total variation, or sorry, SST leads to total variation. SSTR leads to the between sample variation. SSE leads to the within sample variation. And you can see what the SSE is doing is it's just computing the difference between each observation and its respective sample mean. So this is just the numerator for variance within each of the samples directly. So in the traditional definition of that, of variation. All right. And we can see from equation 2 that SST, so the total sum of square, is equal to SSTR plus SSE. So what we're saying, or what we are actually doing here, is we're taking total square deviation and breaking it into two components. Those two components are going to allow us to find between and within sample variation, and then we compare those directly to get to make a determination about whether or not the population means are different. Okay, and equation 2 is called our one-way ANOVA identity. And this idea is the same for all kinds of ANOVA. You start with SST and you just decompose it into different types of sum of squares. And then you can use those different sum of squares to find different types of variance, and then you compare the variance. But this is the simplest case. We're just going to basically further decompose total variation in each of the subsequent lecture sets. Any questions? All right. So we can compute all of those sum of squares just from the raw data. We can do them using the defining formulas, which are what were shown above, or using computing formulas, which are typically a little bit easier to handle. So you can see from the computing formulas that essentially the path that we are going to take is to first find SST. That's because SST is directly or is exactly as we have seen variance defined before. So it's simply the numerator for variance for the entire data set as if it was one whole thing. The SSTR is the second easiest value to calculate. So you can see here we have TJ squared. So that's the total of each sample squared divided by NJ minus the values in that sample squared over little n. And then the error is simply the difference between SST and SSTR. Okay. So the computing formulas would be how I recommend going about finding the sum of squares that we require for each of the different, for the data sets that we're going to be working with. You can use the defining formulas as well, but obviously by hand, that's going to be very tedious. Right. And again, the definitions for each of the components given above are shown on slide 21, but we had to find these earlier when we looked at data layout for the one-way ANOVA. Okay, so we're going to look at the setup for the hypothesis test now. So the one-way ANOVA asks, is there evidence of a difference among the population means? So what's nice about a one-way ANOVA is that our null and alternative hypotheses are always going to have the exact same structure. The only thing that's going to differ is the number of population means or the number of levels in the experiment that we are studying. So in general, we would write H0 mu1 equals mu k. So mu1 equals mu2 equals mu3 equals mu4 equals mu k. The alternative will always be not all means are equal. You could also say a difference exists among the population means. The point is, all we are looking for in this hypothesis test are two population means that are the same. If you have, or two population means that are different. If you have 10 population means and 9 of them are the same and only one is different from one other mean, that's enough to reject the null. But we'll come back to that point later on. Okay. It's just important to recognize that the alternative is not mu1, not equal to mu2, not equal to mu3, not equal to mu4. That's incorrect. The alternative is that a difference exists among any two population means within the experiment. All right. So to compare or to find evidence of a difference, we're going to compare those two variations I discussed before, the within sample variation and the between sample variation. So those are found using the SSTR and the SSE. So you can see here we have treatment mean square. The treatment mean square is the between sample variation. Okay, so okay, so the treatment mean square is the same thing as between sample variation, which is why in some textbooks, instead of writing SSTR, they'll write SSB, and instead of writing SSE, they'll write SSW, so between within. But these are all the exact same thing. So the between sample variance is the mean square treatment, and the within sample variance is the mean squared error. Okay, so these are the same thing. So our F statistic is simply a ratio. So the test statistic is simply a ratio of the MSTR to the MSE. So we're basically just saying if the within sample or if the between sample variance is big compared to the within sample variance, there's evidence to reject the null hypothesis. If the between sample variance is small relative to the within sample variance, then there is not evidence to reject the null. This is essentially how we operate, or this is how we operate going forward. Okay, so we kind of already know the answer to this question, but is the hypothesis test for the one-way ANOVA one-sided or two-sided? Well, we know from the structure of the F distribution that it's likely the case that it's one-sided because we're always going to test in the upper tail. But we can also show that it's one-sided simply by considering the type or considering the structure of the test statistic. So the test statistic is a ratio of MSTR to MSE. So basically, if the MSTR is much bigger than the MSE, the F value is going to be really large. And if the F value is very large, there's a difference between the means. If the MSTR is much smaller than the MSE, the F value is going to be very small, and therefore we do not have a difference between the population mean. Okay, so it's a strictly positive quantity where a big positive value would indicate evidence against the null, and a small positive value would indicate evidence or no evidence against the null. To determine what is big and what is small is where the critical value comes into play. So the critical value is essentially going to define the cutoff between what we consider to be a small and what we consider to be a big test statistic. But from that point of view, it works exactly like any other hypothesis test. Right. It's helpful to summarize our test statistic calculation using what is called an ANOVA table. And an illustration of the ANOVA table is shown on slide 24, and I'll show other examples of this momentarily. Essentially, on the ANOVA table would be what you insert into the hypothesis test on step 3 when you compute the test statistic. So the ANOVA table allows us to structure all of the different values we require in order to compute the test statistic. You can see that there is a horizontal bar here. That means add. So this is telling us that the DF treatment plus the DF error is equal to the DF total, that SSTR plus SSE is equal to SS total, and that's it. From that point, you can see that the table turns into the relationships are that of division. So MSTR is the SSTR over its degree of freedom, and the MSE is the SSE over its degree of freedom. And then the F value, F naught, is the MSTR over the MSE. So the beauty of the ANOVA table is because you know these relationships exist between all of the values in the table, you can actually complete ANOVA tables that only give you certain values of interest. And I'll show you an example of this in a little while as well. Okay, so formally, the one-way ANOVA is run like any other hypothesis test. We start by checking those 4 assumptions. Assuming the assumptions are intact, we state the null and the alternative. We give the test statistic, or we give the significance level. We compute the test statistic, typically done using an ANOVA table. Then we find our critical value or the p-value. Again, you don't have to do both, but I will demonstrate both so that you have examples. And then you make a decision about H naught, and then you conclude with an interpretation of the test. Okay, so we're going to look at an illustrative example to start, and then we will consider a complete or a completely fresh example where we can work through all of the steps from scratch. Right, so in this illustrative example, we are going to compare the lengths of the minke whales entrapped at each of those 4 different depths. So we are working through the illustrative example that we used at the start of the lecture set. We're going to make an assumption that all of the assumptions are intact so that we can work through the steps and conclude without having to make any caveats. Again, we will come back to assumption checking for the ANOVA in the next lecture set. All right, so under the assumption that all of the assumptions are intact, we have on step 1, H naught, mu1 equals mu2 equals mu3 equals mu4, because there are 4 different depths and therefore 4 population means. Our alternative hypothesis is that not all the means are equal. We're going to run this test at the 1% significance level, so alpha 0.01. Okay, and then on step 3, we're going to calculate the test statistic. All right, so you can see here that we are given the sum of squares directly. So our job is just to fill in the remaining parts of the ANOVA table. All right, so from slide 24, we have the different formulas for the degree of freedom, and then we know that the mean squares are just ratios of the SS square over the DF. Okay, so the first degree of freedom, DF treatment, is simply K minus 1. Okay, so DF TRT, or DFTR, I think is how I've been referring to it, is equal to K minus 1, which is 4 minus 1, which is 3. The DF error is equal to little n minus k, which for us is 101 minus 4, which is 97. Okay, and the DF total is equal to n minus 1, which is 101 minus 1, which is 100. Okay. Any questions? Okay. All right. So now we can compute the mean squares. We actually only need the mean squared treatment and the mean squared error. We don't need mean squared total because it doesn't contribute to the F statistic. So the mean squares, as you can see here, are the sum of square divided by its DF. So the mean squared treatment is going to be 37.0985 divided by 3. So this is going to be 12.36617. The mean squared error is going to be the sum of square error divided by its degree of freedom. So 87.2896 over 97. So this is 0.89939. 89. And then the F statistic is going to be the mean squared treatment divided by the mean squared error. So that's 12.36617 divided by 0.89989. So that is 13.74182. And then again, this here is the test statistic. Which we can call F0. Any questions? Little k is the number of population means. Does that make sense? So if you go back to slide 9, we have 4 different depths. So that's the number of population means, or it's the number of levels in the experiment. So that's what little k is. That make sense? Okay. And then Madeline, no, we don't need to calculate the MST because it doesn't actually contribute to anything in the experiment. So it's not relevant to computing the test statistics, so we don't actually need to compute it. But it's still helpful to know what it is just in case you need it to maybe work out a sum of square value later on or work out a DF value later on, that sort of thing. But we don't need it right now. Cool. Any other questions? Sorry. Okay, so just like we do with any other hypothesis test, on step 4, we can take a critical value approach or a p-value approach. So I'll illustrate both. Again, you don't have to do both. In this situation, we're going to be using F distributions because they're F tests that we're running. So if we take the critical value approach, we start by sketching out our F curve. Right. And then I'm just going to move this over so I have it for my p-value in a moment. Okay. So we start by sketching out our F curve. Okay, then we mark down where our test statistic or where the critical value is going to fall. So here's our rejection region. Okay, and this is size 0.01. Okay, so we're going to have an F on DF1, or sorry, we're going to have an F on DFTR, DFE, and alpha. Okay, so this is going to be an F on 397, 0.01. Okay. All right, so what we have to do here is we go to our F table. Okay, so in this situation, we have 3 degree of freedom in the numerator, and we have 97 in the denominator. So clearly we don't actually have 97 on the F table. So we round down. Whenever we're working with degree of freedom, we always round down. So that gives us 60 as the next value that we can consider. So we're on 360, 0.01, which is 4.13. Okay. So we're going to use this critical value for our test. But if we reject at this critical value, we'll definitely reject at the proper critical value because we're being conservative by rounding down. So again, whenever we're in a situation where we can't directly get the DF we want, so on T tables or F tables, then we just round down to the closest value. Okay, so we're going to, so we will use F on 360, 0.01, which is 4.13. Okay. And then we can see that our test statistic is 13.74. So our test statistic is well inside the rejection region. So based off the critical value approach, we will reject. Right. Okay, if we take the p-value approach, we're going to mark down where our test statistic is located. Right, so that little green dot there, that's going to be our p-value. Okay, so the p-value is equal to the probability that F on 3 and 97 exceeds 13.742. I'm just going to round because of space. Okay, so same idea. We go back to our F table. Now, we don't have 97 degree of freedom, so we round down again. So we're going to use 3 and 60. So now what we're doing is we're considering this block of values here. The F value is 13.742. Okay. So the F value is going to fit right here. Okay. So it's bigger than the biggest listed value. So that means that the area that's of interest to us is going to be smaller than the smallest listed value. Okay. So our test statistic is greater than 4.73, which means that the area to its right must be less than 0.005. So we can say, since the probability that f on 360 greater than 13.742 is less than 0.005, then the p-value is less than 0.005. All right, any questions? Okay, so regardless of which approach you take, it's clear that we're going to be able to reject H naught. So the test statistic is in the rejection region. We can reject. The p-value is clearly less than alpha, so we can reject. Therefore, we can say at the 1% significance level, the data provide sufficient evidence to suggest that a difference exists between mean minke whale length at each depth. That a difference exists between mean minke whale length sorry, I'm going to say in. Okay, so a difference exists in the mean minke whale length between at least 2 depth levels. So I have at the 1% significance level, the data provides sufficient evidence to suggest that a difference exists in the mean minke whale length between at least 2 depth levels. So the ANOVA hypothesis is telling us that a difference exists across those depth levels. There's going to be at least 2 levels that are different, but we don't know how many are actually different. So this is all we can say for now. But we do have evidence that a difference exists somewhere. Okay. Right. So I'll stop there for today. Just before we go, a couple of quick announcements. So yesterday I sent out the second mini project and the groups. So if you did not get an email from me, but you are supposed to be a part of the group structure for that, please let me know as soon as possible. Assignment number 2 for the lecture is due on Friday. And that is on lecture sets 2 and 3. So that's a hypothesis testing, 1 sample, 2 sample. Assignment number 3 will be due 2 weeks from Friday, and that's going to cover ANOVA and related topics. Next Thursday, we're going to have our first lecture quiz, which will take place during the lecture. I'll be posting practice problems and writing a more formal announcement about that after class, and I'll also go over that announcement on Thursday with you. That lecture quiz is most likely going to cover lecture sets 2 and 3 as well. So the topics that were covered up until the end of assignment number 2. Okay, and that's all I have for today. So if you guys have any questions, please let me know. I have office hours tomorrow morning, and otherwise I will speak to you on Thursday. And yes, the quizzes will be on CrowdMark. Probably the first two quizzes for sure will be on CrowdMark, and then we'll see if we're back in the university in March.